Now, what are the properties of nuclear forces? So, first one is that the nuclear force is short range. That is, nuclear force acts when the distance between the particles, interacting particles, is very small. Okay, so these nuclear forces are applicable when the distance between two nucleons is 2.2 into 10 to the power minus 15 meter or 2.2 Fermi. 10 to the power minus 15 meter is 1 Fermi, so 2.2 Fermi. And the nuclear force become negligible as the distance between the nucleons increases. This nuclear force becomes weaker, and it becomes negligible at a distance equal to or greater than 4.2 Fermi. Okay, so this nuclear force is a short range force, and it is the strongest when the distance between two nucleons is 2.2 Fermi, and as the distance between the nucleons increases, they become negligible, and they decreases, and it become negligible when the distance between two nucleons is 4.2 Fermi or greater than 4.2 Fermi. Next, it is a very strong force. Nuclear forces are the strongest force as observed in nature. Okay, this force is 100 times stronger than the electromagnetic interaction, that is the interaction happening between some charges, whether they are at rest or moving, so electromagnetic interaction, and 10 to the power 34 times stronger than gravitational interaction, force. Now this nuclear force is charge independent. So now we know there are two type of nucleons which are experiencing this nuclear force. One is proton, which is positively charged, another is neutron, which is neutral. Okay, it does not have any charge. But the nuclear force is acting between these two type of nucleons. Okay, so proton forces, proton neutron forces, and neutron force. And it is observed that these three types of nuclear forces is charged independent. Okay, so the nuclear force acting between two protons, one proton, one neutron, and two neutrons, all of them have almost equal values. That is, they do not depend on the charge of the nucleons. Next, the nuclear force is non-central. Okay, so generally, the nuclear force acting between the nucleons has a non-central component that does not act along the line joining the two nucleons. So generally, what we have seen in case of gravitational force or electrostatic force, that those forces act along the line joining the two particles or masses which are involved. Okay, so gravitational force act along the line joining the two masses, and electrostatic force act along the line joining the two charged particles. But here this nuclear force has a non-central component which does not act along the line joining the two neutrons, two protons, or one neutron, one proton. Okay, and this non-central component depends on the orientation of the nuclear spin. That is, the neutrons and protons are also rotating along their axis. Okay, so they have some spin direction upward or downward, and the spin has some orientation. Okay, the non-central component depends on the orientation of the nuclear spin. Now, next is the another property is nuclear force is spin dependent. So it has been observed that the force of attraction between the two nucleons having parallel spin is stronger than force between two nucleons having anti-parallel spin. So what may happen that one nucleon is rotating in such a way that it has, suppose there is one nucleon like this, it is rotating like this anti-clockwise, so it has an upward spin, and the nucleon which is rotating clockwise, it has downward spin. Okay, so it has been observed that suppose now this is one proton, another proton, or one neutron, another neutron, one proton, another neutron, like this. Okay, so suppose one nucleon has upward spin, another nucleon has downward spin. Okay, so there is nuclear force acting between these two nucleons. In this case, whatever value of nuclear force has, it will be less than if both the nucleons have this the spin in the same direction. Okay, so if I have another nucleon which is rotating in such a way that it has the downward spin, then downward spin, then the nuclear force acting between these two nucleons is less than nuclear force acting between two nucleons which have anti-parallel spin. So nuclear force acting between nucleons having parallel spin is greater than the nuclear force acting between two nucleons having anti-parallel spin. Now another property of nuclear force is that it shows a property of saturation. So what is the meaning of saturation? So nuclear forces exhibit a saturation characteristics. A nucleon inside the nucleus does not experience nuclear force due to all the other nucleons present in the nucleus. Rather, it experiences force only due to its nearest neighboring nucleons. So suppose there are these nucleons inside the nucleus. All these nucleons present inside the nucleus. So consider this nucleon. So this nucleon will experience nuclear force only this surrounding nucleons, but not this nucleons. So these surrounding nucleons are the nearest neighbors of this nucleon. So this nucleon will face nuclear force only due to its nearest neighboring nucleus, not the other nucleons which are present inside the nucleus. So this is called the saturation property, that after a certain point a nucleon cannot experience nuclear force. Now we know that another property, we know that the nuclear force is generally attractive force. But and this attractive nuclear force is the strongest at a distance of 2.2 Fermi. But at a very short distance, suppose the distance between the nucleons decreases, then this attractive force become repulsive. Okay. So at a very short distance of 0.5 Fermi or less, even less distance, the attractive nuclear force becomes repulsive, but it remains attractive at a distance of 2.2 Fermi or slightly less than it. But even at a lesser distance of 0.5 Fermi, it becomes repulsive.